Hey, 30-2s. What we're going to look at in this lesson is we're going to look at dependent events and conditional probability. Now, recall in the last lesson, we already started looking at this. We looked at independent events and we talked about dependent for just a minute. So remember what it means to be dependent. It means that one event has an effect on the other event. Let's try one of these questions. Students pulling two marbles out of a bag, one at a time without replacement. So the without replacement piece right here tells me that this is a dependent event. There are 10 puce colored marbles and 15 aqua colored marbles in a bag. Determine the probability that the student pulls two puce marbles. Okay, let's write our probability statement. This would be the probability of getting a puce and a puce. Well, since it's dependent, here's how we have to write this. I'm going to go back to our formula sheet. And right here is our formula for dependent. I've got it boxed. So here's how it looks. This would be the probability that the first is a puce times the probability that the second is a puce given that the first is a puce. Okay, I mean, that looks pretty complicated, but it's really not. Okay, what's the probability that the first one's a puce? Well, there's 10 puce marbles, and there's 25 in total. Multiply by, okay, the probability the second one's a puce. Well, we've already taken one puce, so there's only 9 left. And, well, there were 25 marbles, so now there's only 24 left. That's it. And then all we got to do is slam that thing in our calculator. And what's that? Let's divide those both by 30. I think that's 3 over 20, but I'll double check just to make sure. So do you see how it is? How that formula, I mean, it looks kind of complicated, but when you just think about your numbers, it's actually not that bad. Okay, let's try another one. Number 2, determine the probability that both are aqua. Okay, so we're going to do the same thing here. So this would be the probability of an aqua and an aqua. Given that we're not replacing, this would be the probability that the first is an aqua times the probability that the second is an aqua given the first is an aqua. Okay, well, there's 15 aqua marbles out of 25. And now the probability that the second is an aqua, so now I've only got 14 left, and there's 24 marbles left in the bag to select from. Okay, and so again, writing down that probability statement, it's a good thing to do, but sometimes it can just make it seem, I don't know, almost a little more complicated than the question really is, isn't it? And I believe that should reduce to 7 over 20. But again, I'll just check quickly. And sure it is. 7 over 20. Good. Okay, so there's what your formula for dependence looks like. Let's try another one. Bag of treats contains 7 candy canes and 6 marshmallows. A student reaches in and randomly selects 2 treats, one after the other, without replacement. Okay, so again, this is a dependent event. Determine the probability that the 2 treats selected are both marshmallows. So what do we got? We've got probability of marsh and marsh. That's the probability that the first is a marshmallow times the probability that the second is a marshmallow given the first is a marshmallow. Okay, how many marshmallows did we have here? Well, there's 6 and there's 13 treats in the bag, so 6 times 13. And now we get another marshmallow and there's only 12 treats left. Okay, and so there we go. We just simplify this thing down. What's 13 times 12 these days? 156. And let's reduce that in our calculators. And again, my friends, please don't write these things in decimals unless you're instructed to, unless you're told to round. Okay, which is 5 over 26. Okay? Not so bad. So again, this is a very kind of common dependent events question. Not so bad. Now, I've been practicing writing this formula down. It's good. It's going to come up where you're going to want to write it. So keep practicing it, please. All right, number 4. Given that PA is 0.3b, the probability of event B is 0.6, and the probability of event A and B is 0.2, are the events independent or dependent? Again, what we're going to do is we're going to test for independence using our independence formula. And if it's not independent, then it has to be dependent, right? So what I'll do here is, okay, I know the left-hand side here is 0.2%. The right-hand side is 0.3 times 0.6, which is 0.18. So the left-hand side does not equal the right-hand side. Therefore, these things are not independent. Therefore, these things have to be dependent. Okay? So again, that's a good test for independence or dependence. You should know it. Let's do just one last question. Okay, I'm going to give you a second. This is a good one to read. Okay, I'm going to hit pause. I'm going to let you read it and then come on back and let's see what we do. Okay, probably had to read that one a couple times, right? So did I. So you look at that and you go, holy cow, that's worded strangely. And this is when you're probably going to have to use your formula. And that's why I've got typed here, determine the formula as a bit of a hint. Okay, what have we got here? Probability a plane will leave Toronto on time. So Toronto on time is 0.90. The probability that a plane will arrive in Saskatoon given that it left Toronto on time. So the probability that it arrives in Saskatoon on time given that it left Toronto on time is 0.59. Okay, determine the formula in terms of the given variables that represents a probability that a plane will leave Toronto on time and arrive in Saskatoon on time. So I want the probability of Toronto and Saskatoon on time is equal to question mark. And so if I was really confused, which it happens on these crazy questions, is I'm just going to write out my statements like this. I'm going to say, okay, well, look it. That's my formula for dependence I've got written right there, isn't it? So we can write this thing down now. What do we have? Probability of Toronto and Saskatoon on time is going to be the probability of Toronto on time multiplied by the probability I get to Saskatoon on time, given that I left Toronto on time. That's a mouthful, hey? Well, probability I leave Toronto Pearson on time is 90%, and the probability I get to whatever the airport is in Saskatoon. They got airports in Saskatoon? Oh, that was a bad joke. Just kidding. Okay, sure they do. Not. And what do we get? The probability that they arrive on time in Saskatoon, given that they left Toronto on time, is 0.531. Again, this is the case where I really want to use that formula because this is confusing when I'm writing it out, like I'm reading this, but it helps as soon as I write my statements out. So when I get a question that's really, really, really confusing to read, I'm going to write out my statements. It's going to help me. Okay, my friends, there is dependent and conditional events done.